So, as we progress towards the end of our course, here we as we told, we are taking a little bit of break from semi definite programming and conic programming and going into a little bit of different stuff, where we are trying to analyze approximate solutions. Approximate solutions are exactly what you basically see in real computations. So, it is good to have a little bit of analysis of them, and one of the main tools that people use in that is a Callant variational principle, which I had outlined in the last lecture. And you observe that here just now before I started the lecture, I changed here this, I had written this as x, which is nothing but a dummy variable, but you might possibly confuse it with this x. So, I change it to z. So, what it says is that if you have an approximate, if the function is bounded below and if there is an approximate minimizer, I can find another approximate minimizer near the current one, such that that approximate minimizer is an exact minimizer of the Potter function. The problem with this Potter function business is that this Potter function is a non-differentiable function because addition of the norm term, and okay. So, that is what would disturb us, but that we need not bother much. Here the example is of that of a convex function. So, here what happens is that if a say like e to the power minus x, such a function like this has a this x is a global is a epsilon minimizer, then y is another epsilon minimizer near x, such that this minimizes this Potter function, which is also a convex function, because you are adding a convex function with a convex function. So, in our case we are just bothered about convex functions. So, we have just our diagrams etc. are all represented through convexity. So, what happens if I have a, so what can we do, what can we say more? So, I have asked the question, what would happen if f is differentiable. In this case, observe that if f is differentiable, what I am having is that I will have a y. So, suppose x is an epsilon minimizer. So, corresponding to x is an epsilon minimizer of f over R n, where f, it goes without saying, is convex. And then what you have to realize is the fact that now what I can figure out using the Callant's variational principle, which I write EVP, that I will have an y such that y minus x. So, instead of y, let me just take lambda equal to root epsilon. So, I will have y minus x is less than equal to root epsilon, epsilon by root epsilon, and y minimizes rather strictly So, I am taking lambda equal to root epsilon in the EVP, and that will give me so this is what we already have known from EVP. Now, if that is the case, I will apply the optimality condition, which would say that 0 element of del of f plus root epsilon at y. Here, because we are basically getting the norm value at 0, the subdifferential would be nothing but the unit ball. So, by applying the standard subdifferential sum rule, we will have 0 element of del f of y plus root epsilon b. But because let us, if we have taken f to be differentiable again, if f is differentiable, then we have del of f y equal to so this condition becomes 0 element of so there exists w element of b, or maybe this is the way it is written in literature, b, such that note that del, again I am here I am using the fact that del of norm 0 is from here to here I have applied the subdifferential sum rule. Here I have applied optimality condition and here I have applied subdifferential sum rule. And then what would happen is, once you look at this condition, you would immediately realize I can write. So, there must be a omega w in this such that 0 is equal to grad f y plus root epsilon b, which would imply that minus grad f y or grad f y just is equal to minus root epsilon w. So, this would imply that norm of grad f y is equal to norm of w. So, which would imply that norm of grad f y is less than equal to root epsilon. Epsilon is arbitrarily small. So, what it says, there is a very important thing, it says a lot about algorithms. See, when we are trying to minimize a differentiable convex function, we are essentially trying to find a point y. So, if I am trying to find a point y such that grad of f y equal to 0. So, if I am just minimizing f over R n, where f is convex and differentiable, so then what is my aim? Because every critical point is a global minima, I have to find a critical point. Sorry, what is my aim, not name? What is my aim? My aim is the following: to find a critical point of f. So, I have to find a critical point of f because I know that critical point of f is a global minimizer of f because f is convex and differentiable. So, the question would be how to find the critical, how do I find a critical point of f? What I do is I try to start with a sequence point x naught, a vector x naught. So, this is an arbitrary starting point. This is how algorithms are done. And then you check is if not, find another point. But you cannot go on like this, you might not even find a point x k for which you might not even find a point x k for which f of x k would become 0. So, the ideas of algorithm is that you fix up a very small epsilon greater than 0. And let me say my stopping criteria is following, that if I find an x k such that the gradient of f of x k is less than root epsilon, stopping rule. Then I stop and choose x k as my approximate solution, as my solution approximation or approximate solution. It is not the exact solution, but I as my approximate solution which has made me happy, that is all. So, we are basically setting up a threshold barrier, and if something is going beyond that threshold barrier, we are stopping the algorithm, and this is how algorithms are done, because you cannot keep on finding another point for which grad f of x k, say there will be x 1, which is you are trying to find another point x 1 for which the grad of f x 1 you keep on checking, but that is not really fair. If it is not 0, again if you check, if it is 0, fine, you stop, if it is not, yes, stop, no, you have to do something, and you have to continue this process. but how long? You might not even find any x1 which is giving you 0. So, that is why you keep take a epsilon greater than 0 very small and make this as a stopping rule. So, what does now the question is, will I get a point xk which will actually satisfy this? That is what, if my problem is bounded below, that is what Callant variational principle says. EVP says such points do exist. That is, this stopping rule makes sense, that is, you would be able to find possibly a point for which this would be less than root epsilon. Now, that point, you might say that okay, you have generated one sequence of points. How do you know that such a point which would satisfy this would be on that sequence? From EVP you cannot say that that would lie on a sequence, but EVP says that if you take any approximate solution, then in its neighborhood there is another approximate solution where such a result would hold. So, basically what would happen is that if I start with an epsilon solution, then what it shows, you can easily show that if I start with an epsilon k solutions, for example, I have a solution xk going to x bar and each xk is an epsilon solution of f, epsilon k solution. So, I have this pair xk epsilon k. So, xk is epsilon k solution. So, what an xk, suppose xk goes to x bar and epsilon k goes to 0, then f of x would become f greater than f x bar for all as k goes to infinity. So, which means that if I choose points like this, then if it is xk is going to some x bar, that x bar would be the actual solution. But now this point xk is an epsilon k solution. So, what would happen that for a k sufficiently large, xk would be very near f x bar, and then for that particular epsilon k I will get some other x tilde k for which norm of f of x tilde k would be less than root epsilon k, sorry, here I should write epsilon k. See, my indexes are all in the superscript when I am writing a vector, in the subscript when I am writing a scalar. So, that is exactly what I will have. So, I will be able to find a point where it will stop. So, there is a point around. So, it is quite obvious that maybe because the function is continuous, if the grad f is also continuous, because it is a convex function, f is continuous and f is differentiable, grad f is also continuous, there will be hardly much difference between the two norms. So, possibly that even norm of grad f x could be also less than root epsilon k. So, that is why EVP actually says that the stopping rules that we have designed are not really bad stopping rules, they are quite well, they can do pretty well in practice. Now, the interesting part is that here we have assumed differentiability or sub-differentiability, etc., etc., etc. Now, what would happen? We make the problem slightly complex, that is, instead of this I am talking about minimize f x subject to now where f and g I all from Rn to R are convex functions and I have no information. What I know that this convex function f is bounded below on the set of feasible points. So, C, the set of feasible points is given as set of all x in Rn such that g I x is less than or equal to 0 for all x for all I. Suppose I am only given the fact that f is bounded below on C. The question is what can I say? Now, if such a situation arises, it means if it is bounded below on C, there is an x bar. So, if I take any epsilon greater than 0, then correspondingly there is an epsilon solution. Let x bar be an epsilon mean, because it is bounded below, there will be always an epsilon minimum of f. See, whenever a function is bounded below, there is an epsilon x bar which is in C. So, I have to write it more clearly, that x bar element of C be. Now, once you know this, so given epsilon greater than 0, there would exist x bar element of C which is an epsilon minimum of f. So, anyway x bar would exist, and we are just assuming that x bar, that there is an x bar which is an epsilon minimum of f. Now, what does this show? If x bar is an epsilon solution, then the following system should less than 0. If this is greater than or equal to 0, then x bar is an epsilon minimum. So, this system has no solution, because if there is an x which satisfies this for all I equal to 1 to m, and for which this happens, then that x breaks the fact that x bar is an epsilon minimum. So, that would lead to a contradiction to the hypothesis which says that x bar is an epsilon minimum of f. So, this system will have no solution. Then applying either the Gordon's alternative theorem or directly separation theorem, we would have some important thing to do. So, now, so these are convex functions, all this. Now, by applying the Gordon's theorem of alternative or directly the separation theorem, the separation theorem, you will get the following. Okay. Now, we will get the following. So, what would be the following? That there would exist lambda naught lambda element of R cross R m, and in fact not only R cross R m, with 0 not equal to lambda naught and lambda, and they cannot, the whole vector cannot become 0, and in fact lambda naught lambda is element of R plus cross R m plus, such that this would mean that lambda naught into f x minus f x bar plus epsilon plus summation lambda I g I x I is equal to 1 to m. So, this is true for all x in R n. So, once this is done, let us see what can we say more. Now, like anything in convex programming, one important condition that we always expect to hold is the interiority of the feasible set, that the feasible set has an interior. So, for that we assume that there exists an x star for which GI x star is strictly less than 0, the Slater condition. So, let this be an assumption for us, the Slater condition holds. So, if this Slater condition holds, so there exists x hat such that for all I. So, once you know this, what would happen, which means what we will prove that we show that lambda naught is not equal to 0, because if lambda naught is equal to 0, then summation. So, if lambda naught is equal to 0, it would imply from this previous equation, which I can call as star or hash. So, it implies from hash that now you see one of these lambda is cannot be 0, because the whole vector lambda naught lambda cannot be 0. So, one of these lambda is cannot be 0. Now, this is true for every x, take this for, this must be true for GI x hat. So, in particular but as lambda I is greater than equal to 0 for all I equal to 1 to m, and one of the lambda i's is strictly positive, it means that one of the lambda is strictly positive. It means that from Slater's condition, Slater condition we have so these two are contradicting each other. So, what we have here is a contradiction. So, this implies that lambda naught is not equal to 0, and without loss of generality we can take lambda naught equal to 1, just divide by lambda naught on both sides, that is all. Okay. So, what would happen is that, so what would happen? So, I will divide by lambda naught on both sides to have f x minus f x bar plus epsilon plus summation lambda I by lambda naught now I will call this as lambda I bar. So, I will have this would imply f x minus f x bar not x bar, sorry, this is x. This is what I have. Again, if I put x equal to x bar, so this would imply immediately that summation I equal to 1 to m lambda I bar g I x bar plus epsilon is greater than equal to 0. This is an approximate version of complementary slackness condition. We can say have this as an approximate version of, here this is not 0. So, it could be negative, but if I add epsilon to it, this thing, this becomes greater than equal to 0. So, epsilon is such that in general this has to be non-zero, it should have been, if epsilon was 0 it will be greater than equal to 0, and this is because x bar is positive, this would actually combine to give this equal to 0. But here I know that this is only strictly greater than 0, what when x is equal to x bar, what I can say that adding the same epsilon I will get this whole thing to be greater than equal to 0. So, it is called an approximate version of complementary slackness condition. Now, keeping this aside, if I notice that the Lagrangian function is written like this, where this is in Rn and this is in Rm plus, then from the previous equation here, what would I get? That is something one has to see, what would I get? I would get the following. From here I will get fx plus summation I is equal to 1 to m lambda I bar g I x minus epsilon is greater than equal to f of x bar. So, it is this inequality will lead me to this. So, this will show what? This will now, since summation lambda I bar g I x bar is less than equal to 0, I can always add this to this. So, if I add a negative quantity, it will drop, the value would drop from f x bar. So, f x plus summation I is equal to 1 to m lambda I bar g I x minus epsilon is greater than equal to f x bar plus summation lambda I bar g I x bar. Once you know this, you know what you have got. You have got L x lambda bar minus epsilon is greater than equal to L x bar lambda bar. So, or in other words, L x bar lambda bar is less than equal to L x lambda bar minus epsilon, as this is true for all x in Rn, this is also true for all x in Rn. Now, so you have got something quite interesting from here, some interesting feature you have got without any assumption of differentiability, nothing, looks what you can call an some sort of strange looking saddle point thing. Now, again let me write down this equation. Take any lambda I, greater than equal to 0, then f x plus summation I equal to 1 to m lambda I g I x, sorry, f x bar plus lambda I g I x bar, g I x bar is a solution. So, is an approximate solution. So, x bar is in C. So, this is less than equal to 0. So, this whole thing is less than equal to 0 minus epsilon is less than equal to, now this thing is less than f x bar because this is a negative quantity. So, it will become f x bar minus epsilon, which is less than equal to f x bar plus summation lambda I bar g I x bar. Here is where we have applied this point, we have applied the approximate, here to here we have applied the approximate version of complementary slackness condition. So, this is the point we have applied the version of complementary slackness condition, and as a result of which this will immediately show us the following. It will show that L x bar lambda minus epsilon is less than equal to L x bar lambda bar. So, some sort of saddle point result we have. What we have is that whenever x bar is an epsilon minima, I could show the existence of a lambda bar in R m plus such that sorry, here it was a plus epsilon, I made a mistake here in the calculation, plus epsilon, because this was minus f x which went there, sorry. So, here it was a plus epsilon, so this would be a plus epsilon, so here it would be a minus epsilon. So, kindly check this thing, because if you look at this thing, there is a plus epsilon here. So, now what I got is something like this. For all, this is true for all x element of R n and for all lambda element of R m plus. So, this is what is called the epsilon saddle point conditions. Let me tell you, this is a necessary condition, this does not give you sufficiency. Anything which satisfies the epsilon saddle point condition is not necessarily an epsilon optimal point. We will come to that slightly later. It is pretty slightly interesting, this part is, and so it is just a necessary condition that if I have a epsilon solution, this is what I will get. Now, if you look at this condition, what does it say? That so if x bar is an epsilon mean of f over c, then there exists lambda bar such that x bar is an epsilon minimum of L x lambda bar over R n. This would simply mean that 0 would element of which so this is an optimality condition, which is a necessary optimality condition. Now, can you write something better from here is not really possible, because we have not studied some rules for this sort of subdifferentials, but what we can say is that there exists another y bar. So, such that norm x bar minus y bar is less than equal to root epsilon, y bar is an epsilon mean of lambda x of L x lambda bar, and 0 is element of del L x lambda bar, del is with respect to x, sorry, del at y bar plus root epsilon norm b. So, this implies again by applying the sum rule 0 element of del of f I bar plus summation lambda I bar del of g I y bar plus root epsilon norm b. So, what I have written down here is actually a necessary condition. Now, if there is an y bar or an x bar which satisfies this, the question is, will that y bar be an epsilon solution? That is quite a natural question to ask. So, that is something we should also like to investigate. We would like to remind that if this condition is a necessary condition, it is really not a sufficient condition. So, if you figure out something like this, okay, you look at not only at the subdifferentials themselves, but you look at some at some flattened set of this particular subdifferential sum, and then you found 0 to be there, 0 may not be exactly in here, but 0 is there, then what would happen? So, then can you tell something? So, that would be an important thing, that let us try to figure out what would happen if I have this. So, what I know is, suppose there exists a y bar element of C. Oh, I have missed something here, I have missed something. Here you cannot say, right, tell G, right, I did not miss anything here, it is fine. Suppose I have something like this, I have written the G. So, sorry, I thought that I missed the G here. So, now I have written this. Now, I suppose have an y bar element of C, which is such that, and epsilon greater than 0, such that I know that 0 is not exactly in this set, that is del f y bar plus summation lambda I bar. There would exist y bar element of C epsilon greater than 0 and lambda I bar greater than or equal to 0, such that, so it is not exactly in this set, but in this set, the flattened set. Then what can I say about f? What is y bar? Right? Then if you try to figure this out, you really have to apply the convexity of these things. So, let me try to figure it out. So, what does this mean? So, there exists V element of del f y bar, Vi element of del Gi y bar, and W element of B bar, such that 0 is equal to V plus summation lambda I Vi plus root epsilon W. Now, this would imply by very definition of convexity in the subgradient, that for any other y in C, f y minus f y bar Now, you see this condition that we have derived this condition from the saddle point results, but the saddle point results is not just this. The saddle point result also has this additional fact that we always also get that summation I is equal to 1 to m lambda I Gi x bar, this one lambda I bar greater than or equal to 0. This is something we always have. So, this is something we have to keep in mind. So, we not only take this condition, we also add this condition. So, this is one condition we have, plus this condition is condition 1, and also let us take this approximate version of complementary slackness. This is greater than or equal to 0. Oh, I think this line is getting up, so let me write it properly. So, it is epsilon plus summation lambda I bar Gi y bar is greater than or equal to 0, I is equal to 1 to m. So, now what I do is do the same sampling. So, I have f y minus f y bar plus summation lambda I bar Gi y I equal to 1 to m minus summation lambda I Gi y bar I is equal to 1 to m is greater than V plus summation lambda I Vi I equal to 1 to m y minus y bar. But this thing is by Cauchy-Schwarz inequality is greater than norm V plus summation I is equal to 1 to m by Cauchy-Schwarz, which I expect all of you to know, those who are viewing it. So, this is nothing but root epsilon w. So, it will become minus of right. This is what you will finally get. So, basically because norm w is greater than equal to 1, here what we, if we had written here as this is equal to minus root epsilon w. So, it will become minus of root epsilon norm w norm y bar. Okay. So, from here you will see that I am unable to, here this norm y minus y bar term comes in, and then I am unable to adjust the thing to get something that as to make y bar becoming an epsilon solution. So, because of this term I am unable to make any adjustment, because norm w I know only is less than equal to 1. I do not know what would happen if it is something else, right. So, what I am minus norm of w is greater than equal to minus 1. So, from here what I can do at the maximum is this is greater than minus root epsilon of norm y minus y bar, this is what I can have. So, what I can have from here is as follows, that f y plus summation lambda I bar g I y, this is greater than equal to f y bar plus summation lambda I g I y bar, lambda I bar g I y bar plus root epsilon y minus y bar minus root epsilon y minus y bar. Now, this is of course, I can, this whole thing is less than f y. So, I can write f y minus f y bar is bigger than, what did I have? What did I have was the following. I had that epsilon, because of that result I had this thing is greater than minus epsilon, this whole thing. So, I will have minus epsilon minus root epsilon norm y minus y bar. So, I can write this as f y plus root epsilon norm y minus y bar, f y bar is greater than minus epsilon, but here if you in case of y put y equal to y bar, this part will vanish. So, I can also write here root epsilon norm plus root epsilon norm y minus y bar. So, what it shows is that this is some sort of a different sort of a minima. One can also define an approximate minima of this form. So, we can say an approximate minima of the second type if you have f of x plus root epsilon x minus x bar minus f x bar is bigger than minus epsilon, then x bar is an approximate minima of the, so x bar is an approximate minima of the second type. So, the condition that I got here is not really a sufficient condition, it is a necessary condition. So, we will not discuss much more into this, we will go into other aspects. So, tomorrow we will discuss very interesting topic, what is called, what do you mean by a descent direction when the convex function is non-smooth. So, this will lead to algorithms using subdifferentials. Thank you.